Hi, and welcome to our talk on distributed XGBoost-Ray. My name is Kai, and I'm a software engineer at Anyscale. I'll be holding this talk with Michael Mui, who is a senior software engineer at Uber. We divided this talk into two parts. First, I'll be talking about XGBoost-Ray. I'll start with a quick motivation and recap, after which I'll introduce the general architecture and the features of XGBoost-Ray. Then, Michael will talk about XGBoost-Ray adoption at Uber. So there is a number of existing solutions for distributed XGBoost training, for instance on Spark, Dask, and Kubernetes. But most of these are lacking important features. Spark, for instance, uses a static computation graph, which does not work well with dynamic scheduling decisions we might get during hyperparameter optimization. Related to that, the existing solutions don't offer good fault tolerance handling. You usually just restart the training run when something goes wrong. Some implementations don't support GPUs very well or at all. And lastly, it's not easy to make them work with the hyperparameter tuning libraries. With XGBoost-Ray, we try to address these issues. XGBoost-Ray leverages the Ray actor model to implement stateful training workers. This, in turn, enables us to implement advanced fault tolerance mechanisms where actors can retain their state even when other actors die. XGBoost-Ray comes with full multi-node, multi-GPU support. We implemented locality-aware distributed data loading for distributed data frames such as Modin or Dask. And lastly, we integrate seamlessly with Hyperparameter Optimization framework RayTune. Before we head into the architecture, let's very briefly recap on how XGBoost and distributed XGBoost works in general. So XGBoost is a gradient boosting algorithm, and this means that at each iteration a new simple model is trained. These models are often decision trees, especially for classification, but they can also be linear models. And then, at each step, the next model tries to fit the residuals of the combined previous models. This optimization is done via loss gradients, and in the case of XGBoost, using second-order Taylor approximations. By adding more and more models, we are slowly refining the model ensemble to give a better and better fit. Distributed XGBoost takes a data parallel approach. This means that each worker shares the same model but trains on a different part of the dataset. The yellow boxes in the figure represent the dataset and its partitions. Workers are represented by the green boxes. Each worker independently trains a full model using its available data. The per-feature loss gradients are then communicated, synchronized, and merged to construct a full tree of the iteration. XGBoost uses an all-reduce implementation called Rabbit to synchronize gradients. A centralized tracker is used to register distributed workers, and it's shown in the red box. Workers then communicate directly with each other and pass their gradients around until each worker ends up with the same information. Let's take a look at the XGBoost-Ray architecture. In this example, we have 4 distributed training workers. In Ray terms, these are all remote actors and can live on the same or different machines on the cluster. The driver first kicks off the distributed data loading. Each worker loads their respective share of data, and this happens in parallel. Next, the driver invokes the native XGBoost.train methods on each remote actor. As discussed, XGBoost communicates the gradients via Rabbit. All we have to do is set up the Rabbit parameter tracking server. The worker with the lowest rank is the designated actor to report evaluation results and checkpoints to the driver. Since every worker works with the same model, this is an arbitrary choice. Also note that this is not a single point of failure. If the lowest rank actor dies, the next actor takes its place and communicates with the driver instead. For distributed data loading, we can load from various sources, such as HDFS or cloud storage like S3 or Google Storage. But XGBoost-Ray can also leverage existing distributed data frame representations, such as Modin data frames. Say, you have 4 nodes and 8 data frame partitions. In this example, they are unevenly distributed. When you start XGBoost-Ray here, it will be aware of the data locality and assign partitions to the workers by node. Thus, each worker will first be assigned co-located partitions. Afterwards, partitions are moved between nodes so that each worker ends up with an even amount of partitions. This is a simple example with an even total number of partitions, but it also works with odd numbers and unfavorable initial data distributions. In distributed training, you will eventually find that some nodes die or get disconnected from the cluster. The default way to handle this is to just restart the training job from the latest checkpoint and for the remaining amount of iterations. Usually, this requires the full training cycle to start anew, including data loading and other setup overhead. XGBoost-Ray comes with two more advanced fault tolerance mechanisms. In non-elastic training, we use a warm restart approach where only the failing actors are restarted and have to reload their data. In elastic training, we even continue training with fewer workers and reintegrate the restarted workers once they are back. But let's get into a bit of more detail here. Let's start with the base case, the simple code restart. First, all workers load their data, and then they begin training. At some point, one of the workers dies. All remaining actors are then stopped as well. We restart the full training job from the latest checkpoint, all actors reload their data, and then all actors begin training again. And it takes some time until it is finished. In XGBoost-Ray's warm restart case, we also start with data loading and training. But once the actor dies, the remaining actors retain their state and their loaded data, and they are just put into an idle state. Only the third actor reloads their data. Training is then continued once the third actor is ready again. It takes about the same time as the cold restart approach, but it invokes much less data transfer. In the elastic training case, we take it one step further. Once the third worker dies, the rest of the workers just continue training. The third worker is restarted and data loading is triggered. The rest of the workers still continue training. Only once the third worker is back is it reintegrated into training again. This will finish much quicker than the other modes. However, since we train on fewer data for some time, there might be performance impairments of the final model. So how grave are those? We ran a benchmark on a production-size classification dataset with 30 million rows and 500 features over 100 boosting rounds. The baseline trains with 10 workers on the full dataset. It shows an evaluation error of about 13.3%. It takes a bit more than 20 minutes to run the training. The fewer workers condition is a sanity check to see what happens if we train on fewer data. We observe a little regression on the eval error, though not by much, and the error seems to get better with fewer data. We attribute this to chance in the random selection of the data partitions. The training time is comparable. If anything, the baseline time might be a bit off. Next, we'll check the non-elastic training. The actors die after about 50% of the training time. The eval error is slightly better than in the fewer workers condition, which makes sense as we continue to train on the full dataset. We sometimes achieve better performance than in the baseline, so generally we can say we are on par. However, it takes almost twice as long to train, mostly because we wait for the failed actors to reload their data, which makes up a huge chunk of the workload. Finally, in elastic training, we can see that our evaluation error is ever so slightly worse than in the non-elastic case, but not off by much compared to the baseline, and usually better than in the fewer workers condition. Most importantly, the training time is basically the same as in the non-failing cases. Thus, at least in the case where we have large shuffled datasets, elastic training can give a great speed up compared to other methods without much performance impairment. For hyperparameter tuning, we worked on a seamless integration with RayTune. Using RayTune, we can start multiply distributed training runs. Each of these trials uses their own hyperparameter configuration. And each trial then starts a number of distributed workers. The workers are scheduled so that workers of a single trial are co-located. This is done to minimize the number of trials impacted by node failures. The integration automatically reports training and evaluation results back to RayTune, and it also saves checkpoints. The integration can also make use of all RayTune features, such as dynamic scheduling decisions like early stopping, or search algorithms like BaseOpt or tree parson estimators. Here's an API example on how to use XGBoost-Ray. First, we'll show a non-distributed training script. After the imports, we just load some dataset, initialize the XGBoost-D matrix, train the model, and save it afterwards. Now, to make it distributed, we only have to change 3 lines of codes. First, we change the import. Instead of importing from XGBoost, we import from XGBoost-Ray. The D matrix becomes the Ray D matrix, which is capable of loading from distributed sources. And lastly, we pass a Ray params object to configure distributed training. Here we just set the number of actors to 2, but we could also use this object to configure fault tolerance. And that's it for the XGBoost-Ray architecture. Next, Michael Mui will continue with the XGBoost-Ray adoption at Uber.
Thanks, Kai. Hello, everyone. My name is Michael, and I'm from the Michelangelo team at Uber, which is our internal machine learning platform team. So building on Kai's introduction to XGBoost-Ray, I'll be telling you more about how we, in collaboration with the folks at Anyscale, bring XGBoost-Ray into Uber's machine learning ecosystem. But before that, I would like to take a moment to provide some context on our broader motivations to bring Ray into our machine learning and deep learning ecosystem, and how it helps us tackle some of the challenges we increasingly observe as we continue to scale machine learning at Uber. I'll first start off with a quick discussion on some of the challenges we see at Uber, how Ray, with a better abstractions for doing distributed ML, can help. Then I will dive into how we incorporate XGBoost on Ray into our ecosystem. Finally, I will share some of the lessons learned and wrap up with some forward-looking ideas that we're thinking about. Here are some of the challenges for distributed ML and DL that we start to see as we scale. Just wanted to point out that Travis from our team has also explored some of these ideas in the Elastic blog, as well as in last year's Ray Summit. So I will encourage you to check it out. First, for distributed training, even with easy-to-use frameworks like XGBoost or Horvath, doing resource-aware scheduling and provisioning jobs still involves setting up the containers and enabling stuff like gang scheduling, are still not that straightforward. And for fault tolerance and auto-scaling, there is a somewhat similar challenge related to dynamic resource allocation and host discovery and orchestration throughout the job, depending on the kind of infrastructure you're running with. Complex computational patterns are also increasingly becoming relevant in ML at large scales. An example of that is distributed hyperparameter search, for which we start to see parallel exploit patterns becoming more common, with each trial allocated a resource or time constraint budget. There are also interest in doing dynamic resource allocation throughout the study, where we combine these exploit models with elastic distributed training, basically saying that we want to be able to fan out during the initial explore phase, and then dynamically allocate more resources to the more promising trials in the exploit phase. Finally, for end-to-end machine learning and deep learning workflows, a common state of the world that we start to see is that we have these heterogeneous computes throughout the workflow, where we may use, say, Spark to do ETL and then distributing, and another framework for doing distributed training. A lot of the efforts end up just provisioning and stitching these bespoke systems together, right? So some questions start to quickly come up, like how do you move data between these stages? Can we take advantage of data locality and somehow avoid having materialized data sets, right? All of these things are complications that start to come up when you're stitching together these bespoke distributed systems. And so this is where Ray starts to come into the picture, right? And just to highlight a few things that we really like about Ray, for one, it's an open framework, it's open source, it runs almost anywhere on Kubernetes, GCP, AWS, anywhere you would like it to run, it most likely already has done the legwork to run there. Two, it also provides a set of general distributed computing primitives, so that just by using Ray and the stateful APIs, we can get fault tolerance and auto scaling of tasks and actors just out of the box. And just one point on shared memory, Ray also holds immutable objects in shared memory so that they can be efficiently transferred across processes and nodes. This is particularly important in distributed settings because, as we know, data serialization and copying are common bottlenecks. And finally, it has a rich ML ecosystem with many out-of-the-box libraries and frameworks built on top of Ray. And Ray2 in particular, which is one of the most popular distributed hyperparameter search framework, comes with Ray natively. And because it leverages Ray's support and for nested parallelism and primitives, a lot of the benefits that we just talked about essentially come for free, and which, as we will see, really helps with some of the challenges we outlined on the previous slide. So at Uber, how can Ray help us out with some of the problems we just talked about, right? So on a very high level, first, a unified backend for distributed training, right? So recently we released elastic hover on array, which allows us to get the fault tolerance and auto-scaling properties to operationalize elastic deep learning, right? So Ray takes care of kind of the dynamic resource allocation and then the discovery and orchestration of hosts. And by moving XGBoost also to Ray, we'll get fault tolerance and other benefits that Kai just spoke about previously. And we get to consolidate distributed training on a unified compute backend, which is one step towards addressing the fragmentation in compute across workflows. Next, we also have a unified backend for distributed hyperparameter search with both XGBoost and Harvard on Ray readily supporting RayTune. This immediately opens up the ability to do some of the latest budget constraint and population-based exploit patterns with dynamic resource allocation over time. And finally, as we start to look ahead, we think that XGBoost or Harvard on Ray plus RayTune plus the recent work on DAS on Ray is something that's very exciting and promising, and definitely a good step towards a unified compute backend for end-to-end machine learning workflows. I'll briefly touch upon this again at the end of this talk. So how do we actually bring Ray and XGBoost-Ray into Uber's ML ecosystem, and what are some of the challenges in doing that? As a starter, we'll quickly walk through what our internal ML system on a very high level looks like, and this is probably pretty familiar. For batch, we have some data lake and a Spark ETL process that will pull the data from the data lake, do some pre-processing, and write it out to our feature store and label store. When a user starts the training job, the job fetches the data from these stores, perform any pre-processing, and then just starts training. And when it's done, it will write the fitted model binary back to our model store, which can then be used in either real-time serving or batch serving. And in our previous talks and blocks, we have talked about how, in an effort to have a unified model representation that guarantees training and serving consistency, we have essentially encapsulated much of this end-to-end lifecycle that we just talked about using Spark's ML abstractions. We'll cover that again in a little bit. Now, this essentially raises the question of if you're doing data processing and transformation in Spark and want to do distributed model training in Ray using XGBoost-Ray, how do we combine these two so that we can efficiently pre-process data in Spark, then let Ray take over to run the distributed execution of some training jobs, which in this case can be a single XGBoost-Ray job or entire hyperparameter search workflow that fan out to multiple parallel jobs. And then after that, to package those fitted models into servable components that can be pushed to production for serving. So this particular boundary between different computes for data pre-processing, model training, and serving, and what kind of abstractions that we can have to encapsulate this is really what we need to focus on when we talk about how we're going to integrate these two components together. And just now, when we said that we encapsulate the entire end-to-end ML lifecycle using Spark's abstractions, what we really mean is that we're using Spark ML's pipeline abstractions to represent each stage of the lifecycle. In Spark ML pipelines, we have concepts such as estimators, transformers, and pipelines, similar to those concepts in the scikit-learn library. So estimators essentially kind of fit on the data frame to estimate or learn the value of some parameters from the data sets. An example of this will be learning the values of coefficients in a linear regression estimator. Then we have transformers, which takes the data from one state to another by transforming it. And finally, we have the idea of pipelines that strings together a sequence of transformers and estimators. Right? So you can imagine within our setup at Uber, we can have a pipeline with estimators that does pre-processing steps, followed by an estimator that does the actual model fitting, and an arbitrary number of transformers that do post-training transformations. I also want to quickly note that Spark pipeline abstractions also serves as our contract between training and serving to guarantee online and offline consistency. A train model essentially is a pipeline model with a sequence of serialized transformers, right? So our prediction service expects that and simply loads the pipeline model and passes in the data to be scored, to be transformed by each stage, and then returns the final prediction. Essentially, to be consistent with the rest of the abstractions that we have, we figure we can encapsulate the complexity of going from Spark to Ray for distributed training and back to Spark within a Spark pipeline abstraction. This also ensures that it respects the servable contracts with the prediction service. So ideally, users shouldn't have to worry about any of the Ray-related knobs, and they should strictly be interacting with the model code, and the rest should be just abstracted away. And so basically, this is what we came up with. This is what we call the XGBoost-Ray estimator, which is an API built on top of the Spark estimator framework that takes in XGBoost-Ray's train function and fitting it directly on a Spark data frame. We would soon see that instead of XGBoost-Ray's train function, the Ray estimator should be able to take in any arbitrary function to be executed remotely on the Ray cluster. But for now, we'll just use XGBoost-Ray's train function as an example to start. In this example, as you can see, we first import the train function from XGBoost-Ray, specify the config and hyperparameters required by regular XGBoost, and pass it to the Ray estimator. And then we construct a regular Spark pipeline that includes different pre-processing steps and post-processing steps using regular Spark transformers, as well as our Ray estimators. And then we're ready to fit this entire pipeline. We'll simply call pipeline.fits as usual, and then we get a fitted model. Using it, we can then transform the test data sets to produce the final predicted data frame. You'll notice that we're only using a few lines that has anything to do with Ray, right? So the vast majority of this is still standard XGBoost or standard Spark, right? So we essentially are able to reuse the Spark pipeline abstractions that does distributed training without introducing any special concepts, Ray concepts that's exposed to the user. So how do we actually do that? So in our Ray estimator, what's actually happening under the hood is that when you call fits on your training data sets, which is usually a Spark data frame, the estimator will take it and write it out to some storage layer like HDFS or S3. We'll materialize it to the Parquet file format, which is very useful for distributed training overall for a few reasons, such as it supports large continuous reads, so it's very friendly to the storage. It has very fast row queries and provides fast access to individual columns if you only want a subset of your data to go into your final training data sets. This can definitely happen if your pre-processing steps materialize some intermediate columns that you may or may not want to include it. And of course, Parquet files also have native read-write support from Spark, which is important. And after the data is materialized, we'll serialize the remote function that we want to execute. And in this case, that's our XGBoost-Ray train function. Our Ray context will then take the user-specified requirements, spin up the corresponding Ray cluster with the specified number of actors, and each of these actors will start reading different shards of the Parquet files we materialized. Perform distributed training, and then after the job is completed, the Ray driver will fetch the final train model from one of the actors, write it out to storage, and package it into a Spark transformer for serving. And to make this more concrete, I do want to show you an example of how this can be authored by a user at Uber, typically using our workflow authoring framework or within a Jupyter environment. A typical flow may look something like this, where in the first step, you'll create some kind of data processing pipeline composed of transformers and estimators. And in this example, we have string encoders, string and indexer, and string to float encoders. And we randomly split the data set into train tests for cross-validation. And by fitting the pipeline to the train data frame, we get our fitted data pipeline that will transform the raw data into features. But in the next step, before you can start training, we require you to create a Ray context, which allows you to specify the requirements of where you would like to run your distributed training job at. And under the hood, it takes care of spinning up the Ray cluster, provides an entry point to the cluster via the Ray clients that allows us to remotely execute functions on the workers and get the results of those executions back. Right? In this example, we specify the resources we want, number of workers, and what is the custom Docker image we want to use to spin up the cluster. And next, we will define the Ray estimator as we did in the previous example. And with this Ray estimator, we can call fits on the Spark data frame directly and pass in the Ray context as the backend. And again, this spins up the cluster, remotely executes the function, and retrieve the train model binary and package it as a regular Spark transformer for serving. You can also easily persist and reload your transformer objects using Spark's native serialization and deserialization. And when you call save, Spark essentially serializes all the params, the model binary, and basically everything you need to load that model transformer back in the future to do any transformer on other data sets. Previously, we mentioned that our Ray estimator interface should be generic enough to support not only the XGBoost-Ray train function, but really any arbitrary serializable function and execute it remotely on the Ray cluster. Right? So to go from running a single XGBoost-Ray job using our Ray estimator to doing distributed hyperparameter search using RayTune, it should be as simple as providing an entry point like above to the tune run function. In this example, we're doing XGBoost-Ray with RayTune, That's why we're passing XGBoost-Ray's train function as a handle to the tune run method. And the rest is basically similar, where you provide Ray params to specify the job requirements and config, which now also includes parameters related to Ray tune. And now just to kind of tie this back to our initial motivations of, can we combine hyperparameter search and distributed static training in an elastic sense? Meaning that in a time constraint search, can we dynamically allocate more resources to more promising trials to ensure we find the best candidate within the fixed amount of time and compute resources? This is useful, particularly useful to an organization like ours at Uber, where most of our training occurs on fixed size, on-premise GPU and CPU clusters. There are definitely some ongoing work at Berkeley and Anyscale, such as implementing this HyperSched scheduler on top of Ray tune and Ray primitives, and that is precisely going to help us solve this problem. So we are definitely looking forward to exploring these capabilities using XGBoost and Hover on Ray with Ray tune in the near future. And just to wrap up, we move towards elastic hover and XGBoost on Ray for fault-tolerant auto-scaling distributed training. With Ray tune integration, we have now a unified distributed hyperparameter search experience that opens up the latest search patterns, and hopefully in the near future, with something like HyperSched, we can further improve its efficiency using dynamic resource allocation. And these are all steps towards a more unified compute backend for ML and DL. Some other ongoing things that we're exploring, like DAS on Ray for preprocessing, we're also looking into Ray to solve the shuffling data loader issue in deep learning training. So in deep learning training, shuffling is often required to decorrelate the data and improve generalization. But it's expensive at times, especially for large amount of data, because one can only shuffle a portion at a time while being consumed. This portion size ends up being a trade-off between training quality and data loading speed, and we're looking to see if we can use Ray to solve this problem as well. So finally, by standardizing around a unified backend, ideally, we should no longer have any need to maintain or provision separate infrastructure across the end-to-end ML workflow, right? So we don't need to set up a separate Spark cluster or a separate orchestration layer just for hyperparameter search. And two, we should no longer need to have materialized any pre-processing data to disk, so you can potentially leverage stuff like data locality and the co-location of the actors to take advantage of Ray's zero-copy shared memory using the object store. And so that kind of concludes our talk for today. Thank you so much for your time. Please check out the XGBoost-Ray project on GitHub and the documentations we have linked here if you want to learn more. Thanks again, and we're happy to answer any questions you might have. Thank you.